Okay, this is exam 4 for physics 202. I have this circuit sits in a magnetic field, and the magnetic field varies with time, is given by this function. I want to first know what is the rate at which the magnetic flux changes. Well, first of all, my flux is equal to B dot dA. Or actually, we'll just call it B dot A here. Now, my area doesn't change. My magnetic field does change, and the area and the magnetic field are parallel. So this this dot product doesn't have a cosine term in it because the cosine of 0 is 1. So if I want to know how the flux changes, dphi dt, since the area doesn't change, that's just going to be area times dB dt. So that is going to be my area, which is 4 square meters, because I have a 2 meter by 2 meter square here, times dB dt. Now, the derivative of this function is negative 6t. So I'm looking at negative 6 times t, which is 2 seconds. So that's equal to negative 48. Let's see, that's in Webers per second. So that's how my flux changes. That's for part A. That part was worth 4 points, by the way. Now in part 2, I want to know what is the net EMF in the circuit. Now in order to do this, we have to sort of go forward to part C and find the direction of the induced current, or the direction of the induced EMF. Now I have a flux that is decreasing. That means that the direction of the induced magnetic field is going to be in the same direction as the magnetic field that's already there. So I'm going to have a magnetic field that's induced that is in this direction. So this is my induced magnetic field, and the current that causes this magnetic field, then by our right-hand rule, which we did last semester, is going to be in the counterclockwise direction. That means that if I think about this, what kind of induced EMF is causing this current, it's going to be as if I have a battery that's like this, that is at 48 volts. So my net EMF is going to be 48 minus 10, which is equal to 38 volts. A lot of you didn't get this. A lot of you said that it was 48 plus 10, and obviously that's not correct. And it's an inappropriate application of Lenz's law in order to find the direction of this induced EMF. So I gave you some credit for it, but I did knock it off some. All right, at t equal 2 seconds, what is the magnitude and direction of the current? Oh, by the way, this was 4 points. And then at C, at t equal 2 seconds, what is magnitude and direction of the current? So I is equal to my EMF over my resistance. That's 38 volts divided by my resistance, which was, 2 ohms. So that's equal to 19 amps. So I have 19 amps in this circuit due to this changing magnetic field. And then D, if there were 5 turns of wire in the circuit, what would the current be? So it's not just as simple as increasing the resistance. My induced EMF now is equal to 5 times 48 volts. All right, 48 was the induced EMF just for one turn of wire, but now with 5 turns of wire, I now have this, which is going to be 240 volts. And then my net EMF is going to be 240 minus 10. That's 230 volts. That 10 volts was the 10 volt battery that is already in the circuit. And then my current is going to be my net EMF divided by the resistance. All right, but if I have 5 turns of wire, I'm going to call that 5R. So that means 230 volts over 5 times 2, or 10 ohms, and that's going to be 23 amps. All right, part C was worth 3 points, and part D was worth 5 points. Consider this circuit. Here I have a Rlc circuit, a resistor, and an inductor. And I have several questions about it. What is the equilibrium current? Well, the equilibrium current is pretty simple to find. The equilibrium current for A just occurs after the inductor is no longer affecting the circuit. And so that equilibrium current is going to equal to my EMF over my resistance. It's as if the inductor isn't even there. That's 12 volts divided by 4 ohms. That's equal to 3 amps. So that's my equilibrium current. And how long does it take to reach 1/2 of this equilibrium current? So for part B, I want to know how long does it take to reach this, I know that the expression for the current is given by this. This is a lot like what we saw with the RC circuits too, by the way. So the expression is similar, or it's basically the same except for tau L, which is a different value. Here, tau L is my inductive time constant. Tau L is equal to L over R. That's going to be 8 henries over 4 ohms. It's equal to 2 seconds. Okay, so now I'm going to take this. My current is going to be not 3 amps, but 1/2 that, so 1.5 amps equals 3 amps times 1 minus e to the minus t over tau L. I need to solve this. Some of you have trouble solving this, so let me just step through this. So 1/2 over 3, 1.5 over 3, that's going to be 1/2 equals 1 minus e to the minus t over tau. That's going to be 1/2 minus 1, so negative 1/2 equals negative e to the minus t. Excuse me, that's a t over tau, which is 2. That positive, positive. I take the natural log of both sides. That gets rid of that. So I get the natural log of 1/2 equals negative t over 2. Multiply this side by negative 2, this side by negative 2, and I get t is equal to 1.39 seconds. All right, so that's for part B, is 1.39 seconds. And by the way, this was 3 points, this was 6 points. Part C will be 2 points, and this is 4 points. Okay, sketch the function that shows how the current varies with time. Well, if I plot I versus t, it's going to look like this, where it asymptotes at your maximum current, IM, which is 3 amps, which is when that inductor is no longer affecting the circuit at all. Initially, this current is low. Describe in 1 to 2 sentences what happens in the inductor that keeps the current from immediately reaching its equilibrium value. Well, when the current changes in the inductor, the inductor generates a changing magnetic field. So that means that I also get a changing magnetic flux, by the way, dphi dt. So it produces, that is, the inductor produces an opposing EMF. This is our induced EMF to the battery. Right. This impedes the current, or resists the current. Something along those lines. I was looking for this magnetic field and an induced EMF that actually resists or impedes the flow of the current from the battery. That's all due to the inductor. Now you have to have a changing current in an inductor in order for it to produce an EMF, an induced EMF. So once the current maxes out, you no longer get a changing magnetic field, so you no longer get an induced EMF in that inductor. All right, the switch in this circuit is initially closed at point A. So initially, it's like that, and that just allows the capacitor to charge. And then you flip the switch, and you flip it over to point B. And so what I have here is an Rlc circuit with an inductor and a capacitor. And I want to know several things. Just first describe in a couple 1 to 2 sentences the transfer of energy, and then sketch a plot of how the energy varies with time. Okay, well the plot is going to look like this. I have UE, which starts at its maximum. This is UE. This is the energy stored by the electric field in the capacitor. So it starts out with maximum energy. And then UC looks like this. Not UC, I'm sorry, UB This is UB. That's the energy stored by the inductor. So initially the capacitor has maximum energy and the inductor has no energy at all. And then the inductor gains energy as the magnetic field strength increases in the inductor. And while the electric field strength on the capacitor goes down as it loses charge. Okay, so let's put that in words. The energy contained in the B and E fields, in the magnetic fields, and the electric fields, that's in the inductor and the capacitor respectively, remains constant. Let me clarify that. The total energy contained in both the B and E fields combined, that total energy remains constant. There's a transfer of energy then between the two devices. And because you don't have a resistive element, a resistor that causes this damping effect, this goes on forever. So if you had no resistance at all in the circuit, you would have this transfer of energy forever because it would lose no energy. Now, initially, which contains the most energy? I already talked about this. The capacitor has charge. What is the frequency and angular frequency of the oscillations? Okay, well, for part C, the angular frequency is square root of 1 over LC. You have to be careful here with your units. Some of you got this wrong because of that. 0.03 Henrys, excuse me. I always want to call it Herads. 0.03 Henrys because it was 30 millihenries. That's 0.03 times 6 microfarads, so 6 times 10 to the minus 6 farads. Take the square root of that, I get 2360 radians per second. That's my angular frequency. However, I also want to know what is F. F is omega over 2 pi. This is usually what we think of when we think of frequency, and it's 375 hertz. All right. In part D, I want to know what is the maximum value for the current. Well, I know that the maximum magnetic energy is equal to the maximum electric field energy. All right. This is kind of like what we talked about with an oscillating spring last semester, where the maximum potential and kinetic energies are equal. Well, this is going to be 1/2 Li squared equals 1/2 Q squared over C. Or if you want to think about it this way, 1/2 Li squared equals 1/2 CV squared, where V is the voltage that charged the capacitor, either one of these, because these two expressions are equivalent. And then I solve this for I. We'll lose my halves there. So square root of CV squared over L. And that's the square root of 6 to 10 minus 6. V is 10 volts divided by 0.03 henries. And that gives me a current of 0.14 amps. Alright, that's it for D. Now calculate a time when the current is at its maximum value. Okay. Different ways to approach this. I'll show you a couple of ways. So I think about the energy of the magnetic field. It looks like this. This is UB. And I want to know when is the current at its maximum. Actually, no, let's not do it this way. I know that the current, most of you did it this way, which I thought was pretty good. The current is equal to Im sine of omega t. All right, that's the function that I have for my current. In order for that current to be at a maximum value, omega t has to equal pi over 2, or some multiple of that, right? Because let me redraw this. If I draw my current starts here is my, no, I'm sorry, that's not current. Sine of 0, 0. So this is my current. All right. The sine of omega t, it equals here. Sine omega t equals 1 at this point. And in order for sine of omega t to equal to 1, omega t has to equal pi over 2. So I know omega, so all I do is just put in my omega, which is 2360, times t equals pi over 2. And I get a time, I get 0.00067 seconds. All right, that would be here, or you could do twice that, or 3 times that, or 4 times that, but most of you just gave this answer. All right, so that was E. And then what is the current in the circuit at t equal 2 seconds? Well, we just say for part F, I equals I max, that's IM, which we've already found is 0.14 amps, times sine of 2360 times t, which is 2. Plug that in and find that it is 0.136 amps. All right. Let's see, my point distribution here, I did 4 points, 2 points, 4 points, 3, 4, and 3 points on that. Okay, here we go, have an LRC circuit. This is not a forced LRC circuit. This is a passive LRC circuit, so there's no generator on it. Some of you were a little confused about that. Sorry, I need to pause for just a second. Actually, no, I'm going to keep going. So what is the initial charge on the capacitor? Well, here it says it was connected to a 2-volt battery, so that's pretty simple. It's just Q equals CV. That's 4 microfarads times 2 volts. That's 8 microcoulombs. Sketch plot how the charge on the capacitor varies with time. All right, well, I have a couple of things going on. I have the capacitor and the inductor. That's the LC part of the circuit, which is going to oscillate with time. Remember, we're exchanging energy back and forth. But now I also have this resistor, which has a dampening effect on it. So the current, or the charge versus time is going to look like this. It's going to start out big, the initial charge on the capacitor, because it just got charged up. It has 8 microcoulombs on it. It's going to decrease, and it's going to be damped. So it'll look like this. It's going to be damped by an exponential function, and that oscillating is a cosine function. So what is the initial charge on the capacitor? We did that. What is the period in seconds of the oscillations for this circuit? So for part C, you had to find omega prime. And in the course of that, you also had to find omega. So let's go ahead and find omega, which is the square root of 1 over LC, which if you put in those values, I get 177 radians per second. And then I need to find omega prime, which is equal to the square root of omega squared minus r over 2L squared. So that's going to be 177 squared minus r is 500 over L quantity squared, square root of all that, and that's equal to 174. Pardon me. This is my omega prime radians per second. All right, so I want to find the period. Well, my frequency is omega prime over 2 pi. And I know that t is 1, the period is 1 over the frequency, so that's equal to 2 pi over omega prime, which is 2 pi over 174, which is 0.0361. All right, so that's the period. That describes the the time between the successive peaks is 0.0361 seconds. Now, what is the charge after 10 periods have elapsed? Okay, well, I know that Q is equal to Q max, that's at 8 microcoulombs, times e to the minus RT over 2L. I lose that trig function, that sine function, because I'm looking for the charge at these maximum value at one of these maximum values, the 10th maximum value. So I know that that has a value of 1. So I'm just going to lose that right now and just deal with the exponential function. So I have 8 microcoulombs times e to the minus 500 times 0.361 divided by 2 times 8. And that has a value equal to 1 times 10 to the minus 4 microcoulombs. I can keep this charge in microcoulombs. The exponential function doesn't have units, so I just carry over the microcoulombs. And I think that's it. Let's see, so I had 2 points, 3 points, 5, and 5 points on this one. All right, some of those are harder. Here I have a couple easier ones. Here I just want to draw the phasors for each of these. Phasor A looks like this. Phasor A is at a maximum value there that is decreasing. So remember, these phasors move in this direction, and the magnitude, the y component of the phasor, gives the magnitude, or gives the function. So here I'm at my maximum positive y value. Here, this at point B, it's going to be here. This is B, this is A. Part C is in the maximum negative direction. So it's like this, that's C. And then part D is right here, because it's at the origin where I have a 0 value, but it's increasing. Remember, these phasors move in this direction. Each of these was 2 points each, so you had 2 points built in for that problem. All right, here's a pretty simple one for transformer, and then one more after this. For a transformer, remember that the EMF of a single turn is the same for both sides. And so I can say then that the EMF of a single turn, for example, is VP over NP. Right, because the primary voltage as a total value divided by the number of turns will give me the voltage for a single turn. And then that's also true for the secondary side, Vs over Ns. So I have 50 over 16, 15 volts over 16 turns equals Vs over 8. And if I solve this for Vs, I get 25 volts. I am going from 50 volts to 25 volts, so that means that it's a step-down transformer as opposed to a step-up transformer. All right, I did 7 points on this part and 3 points on this part. Rlc circuit. So this is a forced oscillating Rlc circuit. That just means it has a generator and an electric generator. I want to know what is the maximum initial current in this circuit. Actually, I just want to know what is the maximum current. So one of you said that the initial current was 0. I was really just looking for the maximum current. So what is the maximum initial current in the circuit? Well, my current is just equal to my EM, that's my maximum EMF, divided by my overall impedance. So I need to find my overall impedance first of all, and you actually need some of these values for later. My overall impedance, remember by that vector analysis of the phasors, is this. This is just from the Pythagorean theorem. Looking at those phasors like we did in class. XL is, excuse me, not that. XL is omega DL. That's frequency is 60 hertz. So omega is 2 pi f, or 120 pi. So this is 120 pi times L, which is 0.212 henries. That's equal to 80 ohms. So my inductive reactance is 80 ohms. My capacitive reactance is 1 over omega DC. .66 microfarads. That's equal to 40 ohms. And so I can find my overall impedance. C is the square root of 100 squared plus 80 minus 40 squared. And that's equal to 108 ohms. So further then I can find my maximum current, which is going to be my EM, which is 12 volts, divided by 108 volts. This gives me a maximum current in this circuit, which is 0.11 amps. So that's the answer for that part. In part B, I want to know the phase. Remember, it's just simple vector math, XL minus XC over R. That gives me 0.38 radians. Having my calculator in radian mode for that calculation. And part C, just wanted you to write the function, so just take those things and put them in the right function. 0.11 amps, that's my maximum current. Here, let me write that actually. I at a particular time is equal to Im times sine of omega dt plus phi. That's equal to 0.11 amps sine of 120 pi t plus 0.38. That was the answer for there. And then part D, I wanted to know the current at a particular time. Well, just take t equals 0.1 seconds and plug it in there and calculate that, and you find that I is equal to 0.04 amps. And then finally E, draw the phasors. We talked about how these things work. The voltage of the inductor leads the voltage of the resistor, which leads the voltage of the capacitor. Remember our mnemonic, Eli the Iceman. Just help you to remember that. Alright, let's see, point distribution was on this part 5, 3, 3, and 2, and 2.